Hi all, welcome back to the EKS Anywhere saga series with bare metal clusters. I'm joined by my colleague Raj in Dell Consulting Services. Hi Raj.
Hello, everyone.
Well, Raj tells me it's the coldest night where he stays in US. Am I correct?
Yes, the cold front came in today. It's going to be below freezing tonight.
Wow. Okay. Well, with that, on this chilly winter night, Raj is also helping us, deliver this video. We are all set to actually demonstrate a very particular and pervasive use case in the industry when it comes to doing AI/ML pipelines and things like that. Well, it's Kubeflow, and this time around we will actually deliver an end-to-end workflow or an end-to-end experience, right from creating the EKS Anywhere cluster to deploying CSI drivers through our Dell PowerScale. Note that in our previous videos, we've been talking about the kind of beast that PowerScale is, and hence the right fit for coupling it with all our AI/ML abstractions and stack, right, as a persistent storage. So CSI drivers for PowerScale on the bare metal cluster, and then lastly followed by the Kubeflow deployment and a sample notebook actually. So that should actually help you visualize how you could actually run Kubeflow with GPUs on an EKS Anywhere bare metal cluster and coupled by persistence layer from Dell PowerScale. With that said, let me share my screen. Okay, so we do have, let me close this one. Yeah, this is, so these are the three nodes actually, .60, .61, .67, and .68. These are the three bare metal nodes. And as you can see, they are all to start with powered off. Okay, so that we do a clean install. .60 is going to be our control plane node. .67 is going to be our worker node 1. .68 is going to be our worker node 2. If I just browse through the system in terms of 67, which is our worker node 1, so right now it's in a shutdown status, so no information available. Let it come up. So all these worker nodes, which are the two worker nodes, they are coupled with L40S GPU cards. So we'll wait for the cluster to come up. So let's start the cluster run. I am on the EKS Anywhere admin machine, from where if I say cat cluster.config, you can see and recall that our cluster configuration file is a minimal configuration file, stating what is the cluster spec. The version that we will be running is 1.30, and for the worker nodes and the control plane nodes, these are the configuration blocks, right? So a very minimal configuration. For the Tinkerbell data center config, we are using the same machine, the admin machine, as the also the web server. So you can see that this particular server itself is .61. Sorry, my eyesight is a little weak. Yeah. So you can see this machine is a .61 machine, the admin node itself. And then on top of that, we are running a web server, which I told you, I think in the initial under the hood video, that if we decide to run the web server on the same admin node for serving the OS images and the hook OS images, we will have to run it on a different port other than 80 due to a conflict with the Tinkerbell, presenting itself on port 80, for certain bootstrap activities actually. Okay, so basically that's for the Pixie boot and all that. So this is what the OS image URL looks like, and this is where our hook OS is stored. Let's quickly go into the HTML directory and validate the presence of these images. We can see that my HTML directory, where the images are going to be served, has 3 images for Red Hat and 3 images for Ubuntu. We are going to be running 1.30 for Ubuntu. The hook directory is also set up. And under the hook directory, hook OS is required, as you know, for the bootstrapping through the Pixie boot process, the minimal OS. So these are the two files which are downloaded from the official repos of HookOS and then placed here in the hook directory. So all done here. Okay. So we do have the hardware.csv also. And you can see the hardware.csv has the inventory for all the three nodes. Okay, the iDRAC IP addresses, the iDRAC passwords, and then the IP address where these nodes are going to be fetched from. So .60, .67, and .68. These are the IP addresses that Tinkerbell will dole out through DHCP based on the MAC association of all the three nodes. So we can see the MAC addresses here. The first node for this MAC address, this IP combination is going to be the type CP. The other two are going to be the type worker, right? Now with that inventory file set and the cluster config set, we can start creation of the cluster. EKS Anywhere create cluster -f cluster config.yaml -- hardware CSV hardware.csv, and we'll keep the verbosity level as 4. Okay. So this process, I think I don't want to overemphasize on, again, the workflow of actually getting the cluster created. But for now, understand the nodes are in a switched off state. They will go through a typical cycle of, getting a PXE boot done, downloading the HookOS, and then through HookOS, they will actually, do the the Tinkerbell will deploy the, streaming the image of the actual OS and things like that to a point where the node gets ready, depending upon the role, whether it's a control plane node or a worker node. And then finally, the cluster should come up actually, right? And that's going to be the conclusive stage where the cluster is fully created, post which we can actually start our kubectl operations. This entire act will go on for about 35 to 40 minutes. So let me just start the video, start the process itself, and then I'll pause the video and then resume once the cluster is fully deployed. So let's do that. So we can see that the cluster creation has started. Let me pause the video and come back once it's fully ready. Okay, so we are back and the cluster is now fully created. So now the cluster is created. Let's quickly export the kubeconfig. ARD poc5 and let us see if we can access the nodes -o wide. So there we have it. The cluster is fully ready with one control plane and two worker nodes running 1.30 of the Kubernetes version. The Ubuntu OS is 2204. And we can also get some hardware information in the sense of the inventory file that was used actually. So -a, show labels. Okay, so we can see the Tinkerbell provisioner for these nodes here. What else? So this is so right now, if you see, there are no pods in the default namespace. The namespaces which get created by default are these. So this is pretty much standard. Now that we have this, cluster operational, which is our EKS Anywhere on bare metal cluster, let's also look at our nodes, the iDRACs. And now that the worker nodes are up, we can actually look at the GPU cards as well. Okay, so the accelerators. So we can see this is the first worker node, 2 GPU cards, 2 GPUs, NVIDIA L40S. Let's look at the second one. I'll have to re-log in. Give me a minute. Let's look at the GPU cards on the second worker node. So we do have, both of them here. So now first things first, what we will do is before we go ahead, installing the GPU related activities, which is your GPU operator and everything else, we will first start deploying the CSI drivers for our Dell PowerScale. That will be the first act that we will do. So we can log in into our PowerScale just to kind of correspond. Okay. So this is the OneFS UI. So we can see the file system explorer currently has a directory called as CSI. Okay, and these are some of the previous, from a previous run actually that we had created. So what we will do is basically now start deploying our CSI drivers on this particular cluster. So right now, let's export these particular variables, which we will be using during the installation. Okay, I'm going to deploy the 2.10.0 CSI driver version. My PowerScale cluster name is going to be F900-AI. The username is root. The IP address of the PowerScale cluster is 172.28.208.91. Okay, let me just, for now, unshare my screen. Well, I just kind of exported my password, so I didn't want to be on the terminal. So we've finished these exports. Okay, we will take and derive the EKS distro version through use of these commands. Again, this is to resolve the conflict of the KubeVer and the semantic versioning that goes on inside of EKS CTL or the EKS distro. We will clone the helm charts repository of Dell CSI. Do that. We are inside that directory. The helm charts are downloaded. We will just update the values to suit our deployment. And then we will modify the K8's version with the Cube version that is actually there on the EKS distro for the helm chart. We will download the credentials template, a YAML for the secrets that will give us the access to for the CSI drivers to access the cluster. Okay, this is just the template download. Through the variables we exported, we will update our credentials file. Let's do that. And then finally, we will create the secrets for PowerScale in our cluster. Okay. Again, like I said previously, in this case, we're just doing a base and 64 encoded secret. Feel free to kind of encrypt these secrets or use Vault, with the secrets management. So that's something that is advised for production use. Finally, we will get into the helm charts directory and we will install our CSI driver. Okay. Let's look into the kubectl get namespace. We can see the namespace has popped in, CSI-PowerScale. Let's get the pods in that namespace. Okay, so the node drivers are up. The controllers are coming up. So we'll just wait for this to happen. While this happens, we will create the storage class, or actually let's wait for these containers to get populated. So you can see that the CSI driver, I mean, it's like a couple of minutes, of the entire deployment of the CSI driver. So the drivers are running, and that should give us, access to creating the volumes on PowerScale through these CSI drivers. For that, we need a storage class. So we will retrieve a template for the storage class. And then we will patch the storage class as the default storage class, given that our Kubeflow components will expect, creating persistent volumes through the default storage class. Else we can update the Helm values in Kubeflow charts, or manifest. But right now I'll just, patch our storage class itself as default. So here it is. So you can see the default storage class is PowerScale. The provisioner is CSI isilon.delimc.com, which is our CSI drivers. And this is the agent. Yeah, okay. So we've got this going now. Okay. Next up, we will install Homebrew and customize. These are required actually for deploying Kubeflow. So let's first install Homebrew. Okay. So let's go ahead and download the installation script for Homebrew. Sudo. Okay. Sudo is working, so yeah. Okay, one important thing, okay, this is a mistake. So yeah, let's take this particular command. Let's install first. Okay, so let's install Homebrew. Okay, while this happens, I'll unshare, I'll stop recording, and then resume once the Homebrew is fully installed. So Homebrew is installed. Now we can install customize to brew. Let's do that. Clear this. Okay, I have to source, update my profile. So let's install customize. So since now customize is installed, and we'll need customize for the Kubeflow installation. The next task would be actually to go ahead and install the NVIDIA GPU operator. So we will just add the Helm repo and then install the GPU operator. Again, I'm not going to detail out, the advantages, the nuances, and the benefits and things like that. We've done a separate video blog on that. Hopefully, you can actually, get some insights. So for now, we'll just go ahead and install and validate once our GPU operator kind of, pops in fully and ready to be executed. Okay. So let's validate if our GPU operator pods are running. Okay, so we have all the respective pods that are required, the device plugin, the CUDA validator, the drivers, the operator, the feature discovery, GPU feature. So everything is intact, nothing has errored out. So now we have our cluster ready to deploy any kind of GPU-based applications actually, right? So we've got this done. Now we can go ahead and deploy MetalLB, since MetalLB will be, for all practical purposes, it will give us that, front end actually as a load balancer for any services which are of the type load balancer. So let's go ahead and install MetalLB. Take this. and deploy MetalLB. So the MetalLB help chart is deployed. We will just observe if we can get the pods, if they are running. Okay, so MetalLB is running. Now we'll configure MetalLB with the L2 advertisements with a two IP address pool, .75 and .76. Well, that's what we have to spare in our lab. So we'll take this and deploy the L2 advertisements that will be doled out from the pool. The IP addresses will be doled out to the services that come up on the cluster as the type load balancer, right? So we have now MetalLB configured. Now the next task obviously would be to install Kubeflow. Okay, so we can go ahead and clone the manifest of Kubeflow. Okay. And then we can just, since we have customized install, we will install Kubeflow. And this could take a little bit of time because of the way the CRDs pop in and the webhooks they run. So I think what we have done is created a while loop so that in case the webhooks are not administered, so we will have to kind of so you can see that they will be retried actually, right? So yeah, let's just wait for this installation to kind of get over and done with, and then I'll resume the video. Okay, so after a couple of retries, once the webhooks are administered correctly, the Kubeflow has been deployed. Let's see what comes up as the namespaces now. So we can see that as a part of the deployment of Kubeflow, we have Istio system that gets installed, the Knative serving. What else is there? The Kubeflow namespace, and whatever notebooks that we create will come up under userexample.com actually. Okay, so yeah, practically we have the Kubeflow installed now. We will go ahead and log in into our Kubeflow. For that, what I've done is I've already taken the kubeconfig file of the cluster, and I've used my Windows terminal actually to just put in here so that I can retrieve the node information and work with kubectl directly from my Windows machine actually. Okay, so we will do a quick port forward and then we will actually start accessing our Kubeflow dashboards actually. Okay, so indeed what we will do is now use the port forward method. Now since I'm on my Windows machine, I'm using my command line here. Sorry about that. Let me just copy paste it properly. Okay. So let me do the port forward. Once the port forward is done, we will access it through the port 8080. So the port has been forwarded. Let's go back to our 127.0.0.1 and port is 8080. Okay. So we can take the default credentials again and the default password. Okay, let's just close this one. Let's create a sample notebook and let's also see, while this is happening, kubectl get ns. I want to show you this kubectl get pods in the namespace of userexample.com or userexample.com. And you can see that there are no specific pods other than the ones that were default, running there. And once we create this notebook, you should be seeing a pod actually corresponding to that notebook popping up in this namespace. And also, if you see kubectl get PVCs in this namespace, you will see that there's no PVC under this namespace, right? So right now we will go ahead and create the CUDA-enabled TensorFlow notebook. Let's keep the memory CPU as 2, memory as 8. And for GPU, we will select one GPU, and GPU vendor is NVIDIA. Again, 5 gig should be okay. What did we name it? Test TF1, let's say that, right? Okay, we'll name it as test TF1, and we will launch. This will take about a minute to get launched. Okay, so let's just wait for it to get launched. So while this notebook is being created, let's get the pods again, and you can see that, a new pod with a suffix of -0 to our notebook name, test TF1-0, and it's in a pod initializing state. If we describe this pod, you would see that the image pulls will be happening as of now. So let's get that thing sorted out. So you can see that this is the image pull going on. Obviously, it's a slightly bigger image, and it's not locally stored. It's being fetched from the repos outside. So yeah, it'll take a little bit of time. So we'll just wait for that. Let's also see the PVC now. Okay, so you can see that earlier there was no PVC, and now for this specific test TF1 notebook -workspace, a new persistent volume has been created with a capacity of 5 gig, and the storage class is PowerScale. If you recall, at SC, our PowerScale storage class, which is the default storage class, uses the Dell CSI Isilon CSI, which is actually the PowerScale CSI. And yeah, practically, we'll wait for the pod to come up fully and do some very, very basic test code and just validate our, notebook, and that's about it. Let's wait for it to completely download the image, and then I'll resume. Okay, so after a while, we've now been able to see that actually the pod is fully running, and obviously it has a persistence, storage along with that. Let's see here. Yes, we can connect to this particular notebook. Connect. Okay, and since this is a TensorFlow CUDA-enabled notebook, we will just write 2-line code just to kind of see if it can access the underlying GPUs. Yeah, let it just pop in. Okay, so we have this one popped in. Let's just start a notebook here. Yeah, I mean, pretty much from here on, you can just go wild and do things what you would typically do, given your experience with, notebooks and things like that. So I don't need to be I'm not the expert there. So yeah, you are the better expert. Our job was to actually, give you a perspective of how do we launch Kubeflow on EKS Anywhere on bare metal with Dell CSI for PowerScale, and then with NVIDIA GPUs, right? I mean, let's run this particular, let's see. Okay, so we can see that the number of GPUs available is 1. That's what we actually gave to this particular configuration for the instance that we created, right? Now, hopefully, that concludes, the entire, where you saw an end-to-end execution of, right, from creating the cluster to deploying whatever is required to eventually, creating a Kubeflow deployment and then an instance, right? From here on, we will hopefully in the near future, we'll bring examples which then exploit the underlying capabilities of the GPU from a Kubeflow perspective, right? Typically things like, building pipelines that run on GPU and things like that, right? So, okay, till that time, thank you.
Thank you. Bye-bye.